A lot of us occasionally hear about calculating Coriolis effect if someone's doing long-range shooting or if there's a long-range artillery. A lot of people know it relates to the spin of the Earth, but I think most people wouldn't have a clue where to begin to try to figure out the Coriolis effect. So that's what I'm going to show here. There's almost no math here. This is mostly just concepts. I already did a couple of videos on Coriolis effect if you're aiming north or south, so you can see those if you want. In this video, I'm going to be talking about Coriolis if you're aiming east or west on roughly the same latitude. Here's some things I figured out. If you're on the equator right here, actually I saw a YouTube video explaining this part. And say this is east right here, so here's the person, here's the target, and let's just say they're on the equator for simplicity. As the Earth rotates to the east, that target's going to rotate down. So let's say we have a situation of a really fast spinning planet and or really low gravity. What this means is if it's a fast spinning planet, this target is going to spin down really fast. And if it has a low gravity, that means this bullet trajectory will be relatively flat. If either or both of these situations are present, then that means as this target rotates down quickly and that flat trajectory of the bullet heads toward the target, the bullet will tend to strike the target at a higher location. So that would mean if you're aiming east, you need to aim a little bit low. And if we reverse this and say the person is now aiming west, so this target is going to spin up really fast, now the bullet will tend to strike the target at a lower location. But this might be more of the situation, I don't know. Let's say we have a planet with either a slow spin and or high gravity. What this means is if the planet has a slow spin or no spin, then the bullet will tend to hit the bullseye of the target instead of going either high or low. Or if this planet has a higher gravity, that means this bullet is going to have a larger arc, or I should say it's going to arc up higher. Then as this target rotates down, the bullet will tend to rotate down with the target, and it may not miss the bullseye by much. Actually, we might be able to make this more intuitive by putting ourselves in the situation. Let's say you're standing on top of a really large barrel or like a really large hamster wheel. They have those at circuses where people run on top of these giant hamster wheels that are on these long arms, so it's kind of fun. And let's say you're throwing some bean bags at a target and this hamster wheel or this barrel is spinning away from you and that target is spinning away from you. What you can do when you throw this beanbag is you simply lob it up and then it comes up and comes down and it's still able to hit the target in the same location. But if you throw that beanbag really fast, so it has a straight trajectory, and this barrel or hamster wheel is spinning really fast, the target will dip down and your beanbag will hit the target at a higher location. Also, I think it helps to look at different scenarios to get an understanding of the situation. First off, imagine that the planet does not spin at all. Then it doesn't matter if this person is aiming east or west, then they'll hit the bullseye. But then imagine if this planet is spinning or starts spinning really fast. This person's bullet or artillery shell or projectile or whatever you want to call it is going to get a push to the left, and so it'll start going faster, and thus it'll cover a longer distance. But at the same time, that target is going to move away from the bullet at the same rate. So it looks like, just from what I can figure out here, whether the bullet is spinning with the rotation of the planet or against the rotation of the planet, its relative motion to the target will be the same and be unaffected. I just said here, theoretically, you could never zero your scope. That is if you're doing long-range shooting, because if you're on a spinning planet, then that bullet is always going to be deflected one way or another. So you can say I have my scope zeroed if I'm shooting directly east, but then once you aim west, it'll change everything. And so you won't be able to zero your scope as if it's a hunting rifle that you're just going to shoot 100 yards out or so. And that's because everything will change depending on which direction you point your rifle or your howitzer. Here's another interesting situation I just thought of. If you're standing somewhere on the Earth and looking due north, straight toward the North Pole, and someone is standing directly to your right, they'll be standing directly due east of you, and you can put your hand out, or you can reach your hand out and touch their shoulder. But if that person continues to travel east from you, they will not stay to your east. They'll actually start heading north, even though they're traveling directly east. So if you want to point to them, you'll have to start pointing north. And so I said right here, someone cannot travel east and stay east of you unless they're on the equator. So right here, here's the Earth. Let's say this is the equator right here, the outer circumference. Here's NP, which is the North Pole. So if you're here, they're here. If they keep traveling east and stay directly east, then they will stay directly east of you. But technically, they'll go down into the ground. If you want to continue to point at them, you'll have to start pointing into the Earth. But if you're up at a higher latitude, here's the latitude line right here. If you're looking directly east, that will follow this dashed line right here. So if you have somebody standing directly east of you and they continue to travel east, that means they'll stay on this east, they'll stay on this latitude line right here, traveling directly east. Now, if you want to point to them, you have to start pointing toward the north. And if they were to stay directly to your east, they'd follow the dashed line and have to start heading south. So what this means for Coriolis effect is, if you're here and your target is at the same latitude as you, somewhere else on the planet, as you shoot an artillery shell toward that target or a bullet toward that target, the bullet will be in the air for a few seconds, an artillery shell will be in the air for maybe a minute or two. By the time that bullet or artillery shell gets to the target, it will have rotated around to the north. So you'll actually have to aim to the north to lead the target. If this was a paper target right here and you're shooting at it and you didn't make any adjustments, then your bullets will start hitting the target to the right of the bullseye. And if the situation was reversed, so you're right here where the target is, and now the target is right over here to your west, you'll have to lead the target by aiming south instead of north. And if you don't lead the target, then your bullets will also hit to the right. But in this case, to the right means they'll be hitting on the north side of the target. So if you take a paper target and tack up somewhere to your east and to your west, and you shoot back and forth, in both cases you will have a grouping of bullet holes to the right of the bullseye. It always helps to make a situation intuitive by putting yourself in that situation. So let's just say this small circle right here is a merry-go-round. Let's say it's a large merry-go-round that is fast moving or fast rotating. You're right here and you have a friend right here on the other edge of the merry-go-round, and you're going to throw a ball to your friend. If you don't lead that friend by throwing the ball a little bit to the center of the merry-go-round, or more in the direction toward the center of the merry-go-round, then you're definitely going to miss your friend because they're going to spin around and miss the ball. And that ball will want to continue in a straight path. I'm not going to be able to do the calculations for this because the target will be dipping over the horizon and going left to the north at the same time. So in this situation, the target is moving away from you. It is moving down as it goes over the horizon, and it's also moving to the left. So there's some three-dimensional geometry going on there, and that makes it pretty complicated. But what I could say, if you are aiming at a target to the east, you could aim a little bit low and to the north if you're on the same latitude. Question mark there because I'm just figuring this out. And you may want to aim low because of the situation over here. Since the target is dipping over the horizon, then you might want to aim a little low to hit it. I have a little globe here for a nice illustration of this. I think it helps if you put the point of interest, let's say this star right here, that compass, put your point of interest where it's horizontal with you, like this. Now, as you can see, as that star rotates, it'll rotate away from you and down and to the left. So I just think that's kind of interesting. So if you were going to shoot this as a target, you would have to aim right over there. So I thought that was kind of fun. So now we know if we're aiming to the east, we have to actually aim to the, if our target is in the east, directly east of us on the same latitude, we have to aim a little to the north. Let's see what this looks like if we're right here and we're aiming at a target that is northeast of us at a different latitude. You can see the other videos I did on Coriolis effect to understand this whole disk idea. But what you can do is imagine cutting the Earth right there where that latitude line is, and you'll have a disk with a certain radius. The larger that disk is, then the faster it spins. And up here at a higher latitude, you have a smaller disk, so it will spin with a lower velocity. And let's say right here is 0 degrees, the equator. And I said right here, if the target is northwest, then that means you need to aim to the north to lead the target. If you look at this picture right here, here's the person, here's the target. The target is spinning around to the north, so we need to aim to the north to lead the target. But then we also need to aim west to lag the target. And that is because this disk right here is spinning faster than the smaller disk that is farther north. So here's the person, here's the target. That little X right there is to the west to lag the target. But that little mark right there also points to the north, where you're going to lead the target as it spins around. Here's some thoughts. I think it would actually be fun to do this experiment. First off, you'd want to eliminate all wind. So you set up a hallway of tarps, like a tarp on each side of the shooting range, and that'll block out all the wind. And you do that for about 800 meters to about 1600 meters, which would be about a half a mile to a mile. And you take all your shots in that direction, say due north. And so you'd have to be somewhere like way out in the desert where you could do this, where you have a long field of view and you can shoot in all directions. But then you rotate your shooting range, say 20 degrees to the east or west, and you fire a whole bunch more shots and get a grouping there. And you just do that all the way around for 360 degrees. And then you could find the displacement of every group for every direction that you shoot. So I think that'd be kind of fun. If you were to make a table with this information, you'd need the latitude, of course, elevation or declination if you're shooting up high or shooting down low. And basically you'd use the cosine of your angle if you're shooting up or down. The velocity of the bullet will barely change due to gravity. So if you're shooting up at an angle, the bullet will slightly slow before it hits the target. And if you're shooting down, the bullet will slightly increase in velocity because of gravity. But the velocity of a bullet or even an arrow is absolutely huge compared to the acceleration from gravity during those 3 seconds or so that the bullet's in the air. So basically you just need the cosine to find out how the angle that you're shooting up or down. So you need the direction that you're shooting, north, south, northeast, southwest, whatever, the distance that you're shooting. You need to get the time that the bullet's in the air, so you might need something like the rifle, the caliber that rifle's chambered for, the bullet mass. Use all that to get the time in the air of the bullet. Altitude, the higher up you go, if you're in some mountains, the air will be a little thinner. I know humidity matters a little bit, but I don't know how much. And I don't know how fine of tuning you could actually do with this in the real world or in the wild, because there's always going to be a little bit of a breeze, almost always. And the wind can blow in different directions at different locations along the bullet path. And that wind is constantly changing velocity and directions. So those are just some thoughts I had on that. It'd be fun to make up a chart like that though. Match grade ammunition for the larger calibers, like the 3.3 at Lapua. Those are around $4 per round. So if you wanted to go out and spend a few hours on a weekend doing some shooting, long range shooting with match grade ammunition, if you shot 100 rounds over a couple hours or so, that'd cost you about $400. So that's an expensive way to spend a weekend, but it'd be a lot of fun. And if you had a little bit of extra money to spend, you could go get yourself a M777 howitzer and fire some artillery shells at 10 or 20 kilometers. That cost you a little bit. On this page right here, I'm going to show what the target groupings would look like if you didn't make any adjustments for Coriolis effect. Okay, so right here we have the bullseye. Let's just pretend we take this piece of notebook paper here and we staple it up to a target board somewhere on the planet. And let's say first off, if we're directly on the equator and aiming to the east, then theoretically this target could spin down and we would hit the target at a higher location. So we'll have a higher grouping right here. Here's the bullseye, here's the higher grouping if we're aiming east on the equator, and likewise, if we're on the equator and aiming west, then we'll have a low grouping. And that is if we don't make any adjustments for Coriolis effect. And next up, if we are aiming east or west and we are at a higher latitude, right here I said aim east or west, north of the equator, and we take this same piece of notebook paper and staple it up on a target board somewhere. It'll look like this situation right here. If we're aiming to the east at the same latitude and we don't correct and aim to the north for the spin of the Earth, we will miss the target to the right, which is the south, and we'll have a grouping to the right of the bullseye. And if we're aiming to the west, then we'll still miss the target to the right because the target will be heading south. And we'll miss the target to the north, which will be to the right of the bullseye. So either way, we get a grouping to the right of the bullseye. And I just had a redundant note here because I don't really plan this stuff out. You can't really zero your scope on a bullseye if you're shooting at a really long range, because you could have your scope perfectly zeroed on the bullseye if you're shooting east, say at 1,000 meters. But once you shoot at a target that's 1,000 meters in any other direction, you're going to have a grouping that is somewhere else. As always, none of this is my field. This is just stuff I figure out because I'm curious. So whenever you watch anything that's educational or listen to anyone talk about anything that's educational or informative, always look for errors. And in the case of my videos, always feel free to point them out. I'm going to do a quick addendum here because Coriolis is so complicated that virtually nobody understands it, and that included myself up until a few days ago when I decided to sit down and try to figure it out. So I'm going to add this addendum here to make this look extremely easy. I actually try to make all my videos look extremely easy so that if a 12 or 14-year-old had basic algebra, then they would even understand them. Okay, so we have two vehicles traveling to the right. Vehicle A is moving at 60 miles per hour to the right. B is moving at 50 miles per hour to the right. But from A's perspective, A is sitting still and B is traveling to the left at 10 miles per hour. If these were not vehicles or trains and instead they were just two spaceships floating out in interstellar space or intergalactic space so that the nearest stars were millions of light years away, then it would be impossible to tell which one of these vehicles was moving and which one was sitting still. All we know is that they are approaching each other at 10 miles per hour. So if person in train A or spaceship A wants to throw a ball to person in train B, here on Earth, train A would have to lag the target, which means A will have to throw that ball out to the left of B. And from A's perspective, that ball will go in a straight line. But from B's perspective, that ball will appear to curve to the right and hit train B. So here on Earth, you would say that train A is lagging train B by throwing the ball behind it and letting the ball catch up to train B. But if these were two spaceships in outer space, you would say that train A is going to lead train B because it appears that train B is traveling to the left at 10 miles per hour. So train A will throw the ball out in front of train B so that train B can hit it. And next page. The reason Coriolis effect appears so complicated is because you're actually merging two models into one. If you separate these two models and look at each individual model as a base model, each model looks extremely simple, but it's when you merge them is when it gets confusing. So right here, let's say we have a planet floating out in space, but this planet is the shape of a cylinder, and it is rotating from west to east. And we have a target right here. So you can imagine as this planet in the shape of a cylinder is spinning, if a person on the sphere wants to hit that target right here, then they're going to have to aim low on that target because this target will be dipping below the horizon. So this cylinder model is extremely easy to understand. But this model only represents the equator. So this is what happens on Earth if you're standing at the equator and you try to shoot at a target directly east or west. But then the cylinder has a side to it, and the side of the cylinder represents what it would be like if you're shooting near the poles, either North Pole or South Pole. So let's take the side of the cylinder off and bring it down so that it looks like a spinning disc or a merry-go-round. Let's say you're right here on the outer edge of this merry-go-round and you're spinning around with a certain velocity, and you have a friend sitting about halfway to the center of the merry-go-round. Your friend is spinning at the same rate as you, but they are traveling at a lower velocity because they're in closer to the center. So if you're out here on the outer edge of the merry-go-round and you want to throw a ball to your friend, so this is you right here, here's your friend right here. So here's you, here's the friend. If you try throwing your ball directly to your friend, That ball will be in the air for about a second or so before it gets to your friend. And during that second or so, your friend will have traveled from here around to this point on the disc. Your ball will travel in a straight line, and so by the time your ball gets to your friend is over here, and the ball has missed your friend. Thus, since you are traveling faster than your friend, you need to lag your friend by throwing the ball behind him or her. But what this will also do is lead your friend, because your friend here will curve around to the north, if this was the North Pole right here. In other words, your friend will curve around the disc. So the ball will lag your friend because you're throwing it behind your friend, but then it will lead your friend because it will meet them right up here as they curve around. So we have two separate models that are very easy to understand by themselves. We have the equator model, which is where you're on the surface of a cylinder, and we have the pole model where you're on a spinning disc. So I think the reason Coriolis effect is so confusing and so few people understand it is because we have two very simple models, but we are merging those into one model. Right here, the two models are separated. They're well demarcated by this sharp edge around the cylinder. And that sharp edge there separates the equator model from the pole model. So what we have to do is actually start smoothing over that sharp edge and making it more rounded. So in this image right here, I've smoothed over those sharp edges and made them more rounded. And as we continue to smooth over those edges, then we get a sphere. So instead of having two very simple models that are separated from each other by a well demarcated border, we have two simple models that are gradually merging into one model, and that's what makes Coriolis confusing, I think.